How are you? And how is your studies and the preparation going on? I hope that you all are studying well and preparing well for the annual examination. Definitely your annual examination will come in the mid of May month or at the end. So you should prepare well. Don't waste of your time. And one more thing, our online classes was started from yesterday onwards. So you please watch all the videos and it will help you. Thank you. And next, today we are going to discuss about an important chapter, acoustics. Acoustics is a branch of physics. It deals with the study of sound waves in solids, liquids and gases. And also this chapter deals about the production of sound waves, transmission and reception of sound waves and the effects of sound waves. But in this chapter we are going to discuss about first one, reflection of a sound wave. Second, echo. And third, Doppler effect. Reflection of sound, echo and Doppler effect. Before we are going to discuss about this topic, first, what is a sound? Sound is a form of energy. Sound is a form of energy. Sound is in an energy form like light energy and heat energy. Like light energy and heat energy. Right. Next, how the sound is produced? Simple. The sound is produced from vibrating bodies. Sound is produced from vibrating bodies. That is, the atoms or molecules in the body vibrates from its mean position. It gives out or it produces energy in the form of waves, which are nothing but the sound wave. So whenever the atoms or molecule present in the body vibrates by receiving energy, about their mean position, they give out the energy in the form of a wave, which are known as sound waves. Right. And next, how the sound is propagated. Actually, the sound is propagated through a medium. Sound is propagated through a medium. Medium means it may be a solid, it may be a liquid, or it may be a gas. Okay, right. So the sound wave can travel through solids and liquid and gases. The sound wave can travel through solid, liquid, and gases. But the sound wave cannot travel in vacuum. So medium is required for the propagation of the sound wave. Definitely, a medium is required for the propagation of the sound wave. Without a material medium, the sound wave cannot be traveled from one place to another place. Right. The sound waves can be classified into three categories based on their frequency. They are, first one, audible sound waves or audible waves. Second, infrasonic waves. And third, ultrasonic waves. So these are the classification of a sound wave based on their frequency. Okay, the classification are audible waves, infrasonic waves, and third one is ultrasonic waves. Right. The sound waves having frequency from 20 Hz to 20,000 Hz or 20 kHz are called audible waves. The sound wave having frequency from 20 Hz to 20,000 Hz are called audible waves. Human can hear this sound, and these sound waves can be produced by vocal cord and stretched strings. Whenever the string is stretched or flapped, it will produce a sound. The frequency of the sound wave emitted from it is from 20 Hz to 20,000 Hz. Humans can hear this sound. So that is why these sound waves are called audible waves. And next, infrasonic wave. The sound wave having frequency less than 20 Hz. Less than 20 Hz are called infrasonic waves. The sound wave having frequency less than 20 Hz are called infrasonic waves. And these waves are produced during the earthquake. The infrasonic waves can be produced during earthquake, and also it is produced from ocean waves. Ocean waves. And human cannot hear this sound waves. But some animals like elephant and giraffe can hear this sound waves. Right. So this is infrasonic. And next, ultrasonic waves. The sound wave having frequency greater than 20 Hz. Sorry, greater than 20,000 Hz. The sound waves having frequency greater than 20,000 Hz or 20 kilohertz are called ultrasonic waves. And ultrasonic waves can be produced by bats. And humans cannot hear this sound, but the animals like dolphins and bats can hear this sound. Right. So there are three classifications of sound wave based on their frequency: audible waves, infrasonic waves, and ultrasonic waves. Audible waves frequency range is from 20 Hz to 20,000 Hz, and infrasonic waves having frequency less than 20 Hz, and ultrasonic waves having frequency greater than 20,000 Hz. Greater than 20,000 Hz. Right. And next we go for comparison between sound wave and the light wave. Comparison between sound wave and the light wave. Already I told, okay, for the propagation of sound waves, a material medium is required. A medium is required. A medium is required for the propagation of sound wave. But for light wave, no material medium is required for their propagation. No material medium required. Right? So without a material medium, light can propagate, but a medium is required for the propagation of a sound wave. Right? And the second one, sound waves are longitudinal waves. It is a longitude. The sound waves are longitudinal waves. Longitudinal waves means if the wave propagates along the direction of vibration of the particles, then the waves are called longitudinal wave. Okay? For example, a wave travels. Suppose a particle vibrates from its mean position like this. The particle vibrates, okay, along this direction from its mean position. So due to the vibration of a particle, the energy is released in the form of wave. Energy is released in the form of wave, which are known as a sound wave. Okay, suppose this wave travels along this direction. Here the direction of propagation of a sound wave is along the direction of vibration of the particle. Along the direction of vibration of the particle. So that is why these waves are called longitudinal waves. So these waves are called the longitudinal wave. So one of the longitudinal wave is the sound waves. Right? The sound waves are longitudinal waves. Longitudinal waves are nothing but the waves which are propagate along the direction of vibration of the particle is known as longitudinal wave. Right? But the light waves are transverse wave. The light waves are transverse wave. Right? Transverse waves means if the wave propagate in a direction perpendicular to the direction of vibration of the particle. Suppose if the particle is vibrated like this from its mean position. here the direction of propagation of the wave is perpendicular to the direction of vibration of the particle. Direction of vibration of the particle. So these type of waves are called transverse wave. Right? Longitudinal waves travels along the direction of vibration of the particle, whereas transverse waves travels in a direction perpendicular to the direction of vibration of the particle. So this is the difference between longitudinal wave and transverse wave. Here sound waves are longitudinal waves and light waves are transverse waves. Right. And third, the sound waves are longitudinal waves, so they are travels in the form of compression and rarefaction. Travels in the form of compressions and rarefactions. Okay, longitudinal waves travels in the form of compressions and rarefaction. Right. So compression means the region where the density and the pressure of the air is more. Rarefaction means the region in which the pressure and the density of the air medium is less. If any wave is travels in the form of a compression and rarefaction, then the waves are called longitudinal wave. So here sound waves are being longitudinal, so it can travel in the form of a compression and rarefaction. Right. Here light is a transverse wave, so it is a travels in the form of crest and troughs. Light waves or transverse waves. Transverse waves travels in the form of a crest and trough. Crest and troughs. The maximum displacement of the wave in positive direction is called crest. The maximum displacement of the wave in the negative direction is called trough. Right? If the wave travels in the form of a crest and a trough, then these type of waves are called transverse wave. One of the transverse wave is light waves. If the waves travels in the form of compressions and rarefaction, then it is called longitudinal wave. One of the best example for longitudinal wave is sound wave. Sound wave. Right. Next, fourth one. And wavelength range of a sound wave is from 1.65 centimeter to 1.65 meter. The wavelength range of a sound wave is from 1.65 centimeter to 1.65 meter. What is wavelength? In the case of a sound wave or a longitudinal wave, the distance between consecutive compressions or successive compression or successive rarefaction is known as wavelengths. For example, the longitudinal wave is travels in the form of compression and rarefaction. This is compressed region. This is rarefaction region. The distance between compression region and the rarefaction region is called wavelength. So wavelength means the distance between compression and rarefaction, or distance between two consecutive compression or two consecutive rarefaction is known as wavelength. The wavelength range for sound wave is from 1.65 centimeter to 1.65 meter. Right. In the case of a transverse wave, the distance between two consecutive crests or two consecutive troughs are known as wavelengths. The distance between two consecutive compressions or a rarefaction is known as wavelength of longitudinal wave or sound wave. The distance between two consecutive crests or troughs is known as wavelength of light wave. Wavelength of light wave. The wavelength range of the sound wave 1.65 centimeter to 1.65 meter, whereas the wavelength range of light wave is from 4 into 10 power minus 7 meter to 7 into 10 power minus 7 meter. The wavelength range of light wave is from 4 into 10 power minus 7 meter to 7 into 10 power minus 7 meter. Right. And last one, the sound wave travels with the speed of 340 meters second minus 1 at 80. The sound travels with the speed of or velocity of 340 meters second minus 1 at NTP. NTP stands for normal temperature pressure. Normal temperature pressure. That is, if the temperature of air is 20 degrees Celsius and the pressure of air is 1 atmosphere, means then it is called NTP. That is normal temperature pressure. So at the temperature of 20 degrees Celsius and the pressure of 1 atmosphere of air, the sound wave can travel with the speed of 340 meters second power minus 1. Right. And the speed of or velocity of light wave, okay, in the air medium, is 3 into 10 power plus 8 meters second power minus 1. So these are comparison between the sound wave and the light wave. Right? A medium is required for the propagation of sound wave. No medium is required for the propagation of light wave. And sound waves are longitudinal waves, whereas light waves are transverse waves. Right? The longitudinal wave, that is the sound waves, travels in the form of compressions and rarefaction. In the compression region, pressure and density are more. In the rarefaction region, the density and the pressure are less. Right? The light travels in the form of a crest and a trough. Crest means the maximum displacement of the wave in positive direction is called a crest, and maximum displacement of the wave in the negative direction is called a trough. Light waves travels in the form of a crest and a trough. Right. Next, the wavelength range of a sound wave is from 1.65 centimeter to 1.65 meter, whereas the wavelength range of sound light waves 4 into 10 power minus 7 meter to 7 into 10 power minus 7 meter. And the velocity of sound wave at normal temperature pressure is 340 meters second power minus 1. And the velocity of light wave in air medium or vacuum is 3 into 10 power plus 8 meters second minus 1. Already I told sound wave cannot travel in vacuum, whereas light can travel in vacuum. So these are comparison between sound wave and light wave. Right. Whenever a particle means atoms or molecule present in the body vibrates from its mean position like this. The particle vibrates like this. The velocity of the particle at every instant changes. The atoms or molecules are nothing but the particles. The particles are present in the body vibrates from its mean position. The velocity of the particle at every instant changes. The velocity of the particle at any instant is given by the formula V is equal to A omega into cos omega t. Cos omega t. This velocity is called the particle velocity. Particle velocity. The velocity with which a particle moves is called the particle velocity. That velocity every instant it changes. It can be calculated by using the formula V suffix p is equal to A omega into cos omega t. Here A, amplitude of the wave, or amplitude of the particle. The maximum displacement of the particle either in positive direction or negative direction is known as amplitude. So A, amplitude of the vibrating particle, and omega, angular frequency of the vibrating particle. Angular frequency. Angular frequency. Angular frequency omega is equal to 2 pi times of linear frequency. 2 pi times of linear frequency. Linear frequency, the number of vibrations produced per second or number of complete oscillations produced per second is called linear frequency. 2 pi times of linear frequency gives angular frequency. Angular frequency, that is omega, is angular frequency of the vibrating particle at t time. Right. So the velocity of the vibrating particle or vibrating atom or molecules at any instant is given by V suffix p is equal to A omega into cos omega t. This velocity is called particle velocity. What is particle velocity? The velocity with which the particle moves is called the particle velocity. Right. Whenever the particle vibrates, which emits or which produces energy in the form of wave, which produces energy in the form of a wave, okay, which are nothing but the sound wave. And this sound wave is travels along this direction with a certain velocity. So this velocity is called wave velocity. Wave velocity. Wave velocity means a velocity with which a wave travels through the medium is called as wave velocity. Wave velocity is denoted by V suffix W. It is given by V suffix W is equal to n into lambda. Here n, the frequency of the wave, and lambda, wavelength of the wave. Okay, product of frequency and the wavelength of the wave gives the wave velocity or the velocity of the wave in the medium. Right. Particle velocity is equal to d sub p is equal to a omega into cos omega t. This velocity continuously changes with the time. But the wave velocity remains constant in a given medium, and it is given by n into lambda, where n frequency of the wave and the lambda wavelength of the wave. Right. And the velocity of the sound wave is different in a different medium. Okay. If the medium changes, the velocity of the sound wave in that medium also changes. Right. And the sound wave travels faster in solid medium than a liquid medium and a gaseous medium, because the solid have more elastic than liquid and gases. If any medium with higher elasticity or more elasticity in which the speed of the sound wave is more, or a medium with less elasticity, the speed of wave or the velocity of the sound wave in the medium is less. Right. So the sound wave travels different velocities in different medium, and the velocity of sound wave is maximum or more in solids than liquids than gases. Right. That is, the velocity of sound wave in solid medium is greater than the velocity of sound wave in liquid medium, which is greater than the velocity of sound in gaseous medium. So sound travels faster in solid and sound travels lesser in gaseous medium. Right. And next, some factors affecting the speed of a sound wave in gases. Some factors affecting the speed of a sound wave in gases. Next topic, the factors affecting the speed of a sound wave in gases. Velocity of a sound wave in gases. And first one, the effect of density. It was experimentally found that the velocity of a sound wave in gaseous medium is inversely proportional to square root of the density of the medium. Square root of the density of the medium. That is, if the density of the medium is more, the velocity of a sound wave in the gaseous medium is lesser. It was experimentally found that the speed of a sound in gaseous medium is inversely proportional to square root of the density of the medium. The gas with the greater density, in which the speed of a sound is less. The gas with lesser density, in which the speed of a sound wave is maximum. So the relation between velocity of the sound wave and the density of the gaseous medium is V is inversely proportional to square root of V. And second, the effect of temperature. Right. It is also found that the velocity of the sound in gaseous medium is directly proportional to square root of the temperature. Square root of the temperature of the gas. Square root of temperature of the gas. If the temperature of the gaseous medium is more, the speed of the sound wave in the gas is also more. If the temperature of the gaseous medium is less, and the velocity value also less. So the velocity of sound wave is directly proportional to square root of t. Inversely proportional means if rho value high, V value less. If rho value is less and V value is high. So V is inversely proportional to square root of density. But here the velocity is directly proportional to square root of temperature. If temperature more, velocity more. If temperature less, and velocity also less. And velocity of a sound wave at any temperature of the gas can be calculated by using the formula P suffix T is equal to V0 plus 0.61 into T. The velocity of a sound wave in the gaseous medium at any temperature is given by the formula P suffix T is equal to V0 plus 0.61 into T. Right. Here V0, the velocity of a sound in the gaseous medium at 0 degrees Celsius, its value is 331 meter per second. Right, V0, velocity of sound wave in gaseous medium or gas medium at the temperature of 0 degrees Celsius. It is represented by V0 and its value is 331 meter second power minus 1. Right? The velocity of sound wave in the same gas medium at T temperature is V suffix T. It can be calculated by using the relation V naught plus 0.61 into T. Suppose if the temperature of the gas is increases from 0 degree Celsius to 1 degree Celsius. That is, if the temperature of the gas is increased by 1 degree Celsius. If the temperature increases, automatically the velocity of sound wave in the gas medium also increases. Now, the new velocity of sound wave in the gas medium becomes V is equal to 331.61 meters second power minus 1. If the temperature of the gas is at 0 degree Celsius and velocity of sound wave in the gas is 331 meter per second. If the speed is, if the temperature is increased by 1 degree Celsius, the speed of sound wave in the same gas becomes 331.61 meter second power minus 1. It means if the temperature of the gas is increases by 1 degree Celsius and velocity of sound wave is increases by 0.61 meter second power minus 1. So for increasing every degree Celsius, 1 degree Celsius of temperature of the gas, and the velocity of the sound wave in the gaseous medium is increases by 0.61 meter second power minus 1. And the velocity of sound wave in the gas at any temperature can be calculated by using the relation V suffix T is equal to V naught plus 0.61 into T. The general relation between velocity of sound and temperature of the gas is V is proportional to square root of T. Right? And third, effect of humidity. Effect of humidity. Right. If the humidity of air is more, humidity is more. If the humidity of air medium is more, that is the amount of water vapor present in the air medium is more, means humidity value is more. If the humidity more and velocity of sound in the air medium also more. So for that reason, the sound wave travels faster in rainy season than summer season. Okay, if the humidity is more and velocity of sound wave in the air medium also more. So velocity is directly proportional to humidity. And next, the effect of pressure. If the temperature of the given gas is constant, if the temperature of the given gas is constant, suppose if the pressure of the gas is increased, the velocity is remains constant. So, if the pressure of the gas is varies, keeping the temperature of the gas constant, there is no change in the velocity of sound wave. There is no change in the velocity of sound wave. So, the velocity of sound wave in the gaseous medium is independent of its pressure for a given temperature. So, these are factors affecting the velocity of sound wave in